Okay, so half-lives. By definition, the half-life is the time that a reaction takes to consume half of the original amount of reactant that it had to begin with. All right, so when you reach that half amount, that's your half-life, right? And if you want to put it in equation format, what that means is that the final concentration at the half-life is going to equal exactly 1/2 of the initial concentration that you started with, right? So A naught divided by 2. All right, and to make it very obvious, we add an extra subscript to the time to imply that this is the half-life. So T1/2, that's the half-life. All right, so what we're going to do is we're going to go through each one of these reactions, the zeroth order reaction, the integrated rate laws to be most exact, of the zeroth order reactions, first order reactions, and second order reactions to derive an equation for the half-life. So let's start with the zeroth order reaction. We have final concentration equals negative kT plus initial concentration. At the half-life, T is equal to T1/2, and the concentration is equal to the initial concentration divided by 2. And so what happens right here is that if you subtract the initial concentration divided by 2 from both sides and add K times T1/2 to both sides, you're going to end up with A naught minus A naught over 2, which is the same thing as saying A naught over 2, right? So in other words, 1 minus 1/2, which is 1/2. And if you divide both sides by K, this gives you the expression for the half-life of a zeroth order reaction. Simply stated, the half-life of a zeroth order reaction is the initial concentration divided by twice the value of the rate constant. Okay, so that's the expression for the half-life of a zeroth order reaction. Now looking at the first order reactions, right, you have ln of A over A naught equals negative KT. I've chosen this particular form because, as you'll see, it's going to get us into a simplified form rather quickly. Remember that at T1/2, right, at the half-life, the final concentration is half of the initial. So that means that regular A is going to have to equal A naught over 2 at the half-life. And now we have A naught over 2 divided by A naught, which means that A naughts cancel out. And what you now have is the ln of 1/2 equaling negative K times the half-life. If you actually plug in 1/2 and take the natural log of it in your calculator, you're going to find out that this equals negative, equals negative ln of 2. But if you want to be most exact, this also equals negative 0.693. So if you divide 0.693 by K, that tells you the value of the half-life for a first order reaction. All right, so ln of 2 is the same thing as 0.693. That might be the better number to remember. It's basically all multiples of 3 if you think about it. But yes, you're dividing that constant by K. And so unlike the zeroth order reaction, a first order reaction has a half-life that doesn't depend on the concentration. It's basically constant. So let's say that it takes you 10 seconds to reach the first half-life. The second half-life is going to take you another 20 seconds. Or excuse me, another 10 seconds. And the third half-life will take you another 10 seconds, and so on and so forth. All right, so that's the half-life for a first order reaction. You can kind of see the difference. For your second order reactions, the half-life, once again, can be derived from the integrated rate law, whereby the final concentration is equal to initial concentration divided by 2. And since this is 1 over final concentration, initial concentration divided by 2, which itself will be divided from 1, is the same thing as saying 2 divided by initial concentration. So here what you can see is that if you basically subtract 1 over A naught from both sides, you're going to end up with 1 over A naught on the left side. And that will equal K times T1/2, which means that the half-life is going to equal the reciprocal of rate constant multiplied by the initial concentration. So here you have it. These are the equations that give you the half-lives for the zeroth, first, and second order reactions. And what you can tell is that as the concentration of the reactant starts decreasing more and more and more, the half-life for a zero-order reaction is going to start getting shorter, shorter, and shorter. The half-life for a first-order reaction will remain constant because it does not depend on concentration. On the other hand, the second-order reaction, which has the reactant concentration on the denominator, as the reaction proceeds forward, you're going to have less and less concentration of A, so the half-life is going to start getting larger and larger and larger. Okay, so some features that kind of affect the overall behavior of reaction, so it's kind of nice to see. But these are the simple cases, and in a particular problem, I can ask you not only to tell me what kind of order the reaction is and what the rate constant is, but I can also ask you to get me the half-life. And needless to say, you first need to get the value of the rate constant, as you can see in these equations, for you to yield the value of the half-life, right? So getting the rate constant is a must. You'll need it not only to answer certain problems that directly ask you about that, but you'll need it to get the values that you will use to find the activation energy. You can also use it to get the values of the half-life itself. Alright, so I'm going to show you an example of how this whole thing plays out. We have the concentration versus time data over here. And if we try to check whether this is zeroth order, first order, or second order, what we need to do is plot the data. Plot concentration versus time and see what we get. So plotting concentration versus time yields something that definitely doesn't look linear. The correlation value isn't even in the 0.9 regime, is way below that, so this is definitely not a line. And what this tells you is that because A over T, or A versus T, doesn't yield a line, this cannot be a zeroth order reaction. So we move on to the next thing, which is to take the natural log of the concentrations. Alright, so taking the natural log of the concentrations, right, you get all these values right here, which once again I would recommend that you do this on Excel or some other program as opposed to doing manually. If you plot ln of A versus T, what you're going to find out is that this actually gives you a really good line. The correlation is basically -1. So this is telling you that this is the best line. You could also you could actually look at the data for 1 over concentration and plot it versus time, but right now I think it's very conclusive that ln of A versus time is the best line you're going to get. So when you do the regression or the trend line for this, you're going to find out that y equals -0.03298x plus 0.8749. And because this is a linear plot, when you plot ln of A versus time, not only is this a first order reaction, but that also means that the rate constant has to equal 0.03298. Alright, and yeah, so here I guess for completion's sake I went ahead and got the values of 1 over concentration, but if you plot that versus time, you're going to find out the line is not as good. So we stick with the first order reaction. So this is first order, so we can use that information to do a few things. First, the half-life for a first order reaction is given by 0.693 divided by K. So if we divide 0.693 by 0.03298, we're going to find out that the half-life is 21 technically minutes, not second. So that's the half-life. Also, we can calculate the initial rate for the reaction. Simply, if you take the rate constant and multiply by the initial concentration, which for this reaction is 2.400, we're going to get an initial rate of -0.0915 molar per second. And so now, as you can see, we got the rate constant, we got the half-life, we even got a rate associated with it. And if you do this at different temperatures, you can find the rate constants at all those different temperatures, which then you can use to find the activation energy via means of the Arrhenius equation. So hopefully this is kind of beginning to wrap your mind around the whole procedure of kinetics. It's actually a very heavy-duty analysis, data analysis that you have to perform, but you know, that's the way it goes with kinetics. Alright, so this is it for this lecture. This concludes the first half of kinetics. In the next video, I'm going to investigate the complex cases, the ones where you actually have more than one reactant. Up until now, everything that we've looked at only has one kind of reactant. So we'll see how we deal with the other cases. Alright, so see you in the next lecture.